this as ring counter. Or shift register counter. So for ring counter or shift register counter, this is a typical application of this shift register. Okay, and the output of this in here, output of last flip flop connected to the first flip flop, flip flop. And this is a typical application of this shift register. Okay, so output of the last flip flop is connected to the first flip flop. So we know the flip flop. Let us consider a 4-bit ring counter now. So 4-bit means we need 4 flip flops. We need 4 flip flops. Okay. So let's consider this case. We are considering D flip flops, which is also JK with that state changing conditions. So let's consider this is your D0, D1, D2, D3. This we already discussed for the case of a shift register, this circuit. And this one is your Q0, that is output of the first flip flop. This is the output of second flip flop Q1 and Q2, Q3. This is flip flop number 1, flip flop number 2, flip flop number 3, flip flop number 4. And as we said, the output of the last flip flop is connected to the first flip flop. So in shift register, we do not have this connection because we just had to shift the data from left to right or right to left. So we don't need this connection from the last flip flop to the first one. And this is again a synchronous counter. So we had to apply clock pulse simultaneously to all the flip flops. This is a synchronous counter. We have to apply the clock pulse. Okay, so this is the shift register, and as you know, this Q0 will be connected to the next input. Q1 is connected to the next flip flop's input. It is connected to the next input. Okay, so this is the diagram, circuit diagram for the ring counter or the shift register counter. This is your clock pulse. Okay, and you also will be having one connection, which is the clear and preset. Clear and preset connection will be there. So preset will be connected to this. Okay, and clear has to be connected to these flip flops. complete this diagram. I will explain this, what are these things. So this is clear, or you can write CLR for clear, not a problem. So we have clear or preset. So this is your preset, and this one is your clear line. So here presetting means we are providing presetting or clear condition through this particular line, and these dots are representing just inversion. Okay, which means that this will be enabled when your clock is in the negative cycle or negative triggering position. Or this we can say this when this line is 0, then here we will be having 1. So when your clock is low, you will be having maximum for this clear and preset option. So at that time that they will be active. So clearing means it will clear all the values or the memories in the flip-flops. Presetting means it will preset value of that particular flip-flops memory equal to 1. Okay, remember that preset will set the value equal to 1. Preset will be giving value equal to 1 to that particular flip-flop output or memory. And the clear option will be giving value 0, or it will clear the memories of that particular flip-flops. Okay, and remember that this when it is this one is 0, here it will become 1, which means that clear will be active. Similarly, here also preset will be active when this is 0. That's why we are putting a dot here, because we have to take the note of that particular value, binary value, or complement of that particular binary value. Now, when you are considering this preset, first we have to consider the preset and we have to consider the clear state. So we will clear all the values in these 3 states, 3 flip-flops. Q1, Q2, Q3 will be cleared, and Q0 will be this particular flip-flop 1 will be having the output which is equal to 1, because Q0 will be 1 because of this presetting condition. So because of this presetting, this Q0 will be equal to 1. Okay. So the first case, in the first case, we are having the truth table for this particular counter. So this will be, let's first consider the clear option, clear or preset. Then we are having this clock. Then we put Q0 at last. So Q3, Q2, Q1, Q0. If clear or preset equal to 0, at that time, irrespective of your clock pulse, Q3 will be equal to 0, Q2 will be equal to 0, Q1 will be equal to 0, Q0 will be equal to 1. Why? Because when you are having this clear or preset which is equal to 0, this entire line is 0. Okay. So when this entire line is 0, here we are having 0. Then you have to take the note of that. Okay, the complement of that we have to consider. Then here it will be 1. When this will become 1, after this complement operation, if it is 1, then which means that the clear command is on. Okay, so we are having clear here. This all these things are clear command, and here we are having the preset. Preset is represented above the flip-flop. Okay, as you can see from this diagram. So when you are having this clear which is on, which means that the clear is having value which is equal to 1, then it will erase all the memory, or it will make this Q1, Q2, Q3 values which is equal to 0. At the same time, we are having preset for the first flip-flop, and when the preset is on, which means that we are applying 0 here, that 0 comes here, you have to take the complement and it will become 1 here, which means that preset is active. So when preset is active, your Q0 will be assigned value which is equal to 1. Okay. So initially, when you are having this clear or preset value, that line, I'm talking about this line, when that is equal to 0, irrespective of your clock pulse, your memory will be changed as 0001. Now, we are considering in the next case, when you're having your clock pulse, we are considering your clear or preset value which is equal to 1. So when this is equal to 1, so when that particular line is equal to 1, what will happen? Suppose this is equal to 1. When this is 1, this one is become 0. Here it will become 0. Here it also becomes 0. This one also becomes 0, which means that clear is not active. Similarly, for preset also, we are having this one will be equal to 1, so that it will be 0 here, which means that preset is also inactive. So now the memory will not change because your clear or preset is that value is set to be equal to 1. So that preset and clear will be inactive at this moment. And what will happen if you are having this negative or this inverted edge of your clock pulse or negative triggering? And in that case, your value from this Q0 will be shifted to Q1. Value from this Q1 will be shifted to Q2. Value from Q2 will be shifted to Q3. And Q3 will be shifted to Q0 through this particular connection. Okay, that we are already discussed this shift register. Okay, for D flip flop, if you are applying what value you are applying, that will be your output. Okay, so in this time you are having Q3 here, and Q3 value is equal to 0, as you can see from this table. Q3 value is 0, so that is 0 here. Now D0 is 0. Okay, so that your Q0 now will become 0 because the output of D flip flop will be following the input that we already discussed. So for D flip flop, if your D value is equal to 0, then your Q output will be also equal to 0. If D is 1, then Q also will be 1. Now in this case, you are having for the next clock pulse, your Q3 is already it is 0. Okay, and that is coming to this first flip flop, and that 0 will come here, so that your D0 is 0 now, and that will make your Q0 0. So in the next, when the negative triggering happens or the inverted edge of your clock pulse comes, this Q0 will become 0, and now Q0 is initially in first case Q0 is 1. So here it is 1. That one will be assigned to value of this D1. So that one will be coming here. So D1 is 1 now. So that D1 will be shifted to Q1. As you know, for the D flip flop, it will be having the same output as input. So D1 is 1 now. So Q1 will become 1. Okay. And then we are having this Q2, which is again 0. Q2 will be taken value from this Q1. Q1 is 0. That is assigned as the input of this third flip flop. And D2 is 0 now. So that Q2 is also 0. And the last flip flop also, this will be 0. And this one also becomes 0. And when you are having the next negative edge of your clock pulse, again this shifting happens. In this case, you are having Q1. Now your Q1 is 1. Now your Q1 is 1, right? Okay, and this one will give your D2 as 1, value D2 as 1, and that will make your Q2 1 for the next pulse, next edge of your pulse, next inverted edge or the negative edge of your pulse. That Q2 will become 1. Q2 will become 1 and all others are 0. Similarly, if you go for the next inverted edge or negative triggering, and you will be having this Q3 equal to 1 because this one will be now input of this last flip-flop D3, and that will be shifted to Q3. So Q3 will be 1, this one will be 0, 0, 0. And for the next one, in all this time, we are considering this clear preset value is equal to 1. Okay. And this time we are having again the next clock pulse edge, so that your Q3 1 will be shifted back to Q0 because now your Q3 is equal to 1. So this is 1. So this line, entire line is 1. Okay, that will be shifted to here. So now your D0 is 1. So for the next clock pulse, your Q0 will become 1. So this Q0 will become 1, 0, 0. Now, as you can see from here, from this table, you can see this particular value which is repeating. I don't know, it is loading now. Okay, so this particular value is repeating. This is the first one that what we considered. Okay, so this set of values which will repeat when you have more pulses, more than 4 pulses, four clock pulses. So for up to this third pulse, it is okay. Then if you are considering the next clock pulses like this, for example, 4 clock pulses if we consider, then that will be 0, 0, 0, 1, then 0, 0, 1, 0, then 0, 1, 0, 0, 1, 0, 0, 0. After that 4 clock pulses, again it will come as 1, 0, like this. So this is again repeating, this set of values which are repeating. Now we are having 4 flip-flops and we are having 4 states. Okay, so for a ring counter, or I will write it on the other side. For ring counter, number of states, or you can say the modes, maximum number of states is the modes. So number of states will be equal to number of flip-flops. So in this case, number of states will be equal to number of flip-flops. So which is equal to 4. So for ring counter or for shift register counter, number of states will be equal to number of flip-flops. If you are using 6 number of flip-flops, then number of states will be 6. Okay, if you are using 10 number of flip-flops, then number of states will be 10. Here we are using only 4 number of flip-flops, so we are having 4 different states, as you can see from here. Okay. So what are the values, decimal values of these counters? So this is nothing but 1, and here this one is nothing but 2, and this one is this is 2 raised to 0, 2 raised to 1, 2 raised to 2, so this is 4, and this one is 2 raised to 3, right? So this is 8. So progression will be like this, 1, 2, 4, 8, like that. Okay, so as you can see from here, it is giving you some random sequence. Okay, so that's about the ring counter or shift register counter. If you draw the clock pulses in the pulse diagram, then we can see, let's say this is the clock pulse. I think we have we stopped here. This period of this pulse, clock pulse should be same. And we have these negative edges. Negative trigger. So and now consider that clear or preset is somewhere here active, and then it is so the clear or preset is initially at 0. That's why I put it like this. And for all other values, it is 1. For all other clock pulses, it is 1. So initially it is 0. At that moment, Q1, Q2, Q0, all values are 0 except Q0. Q0 is 1 and all other values are 0. So let's plot that. Use some different color. So let's consider Q0 first. Q0, Q1. So first I will draw that. So for Q0, first it is 1 when it is at the initial state it is 1 15. So we are having this clock pulse as shown here in this figure. Okay, and we have this clear or preset option. So only after that clear or preset option we are having Q0 equal to 1. So we are actually presetting the value of Q0 to 1, and we are clearing all other values Q0, Q2, Q3. Q1, Q2, Q3 we are clearing so that those values will be 0. And Q0 will be 1 because we are making it preset. So presetting means we are making the value of Q0 equal to 1. So at that moment, we have to consider this particular 0 pulse, as you can see from this figure. That particular portion, from that onwards, the Q0 value will be maximum. That will become 1 as shown in the figure. Okay, and after this edge comes, first clock pulse edge, that maximum value or the 1 which is stored in Q0 will be shifted to Q1. When this particular clock pulse edge comes, that Q0 value will be shifted to Q1. So that the Q0 value will become 0 because Q3 will be shifted to Q0. So Q3 now it is 0, so it will become 0 from here onwards. And after the fourth clock pulse, that is this value, then Q0 again will become 1, and it will be remaining in that state until the next clock edge comes, next negative or inverse clock edge comes. And Q1, if you consider, initially Q1 value is 0, as you can see from this figure, this table. Q1 value is 0. Then for the next clock pulse, it is coming 1. For the first clock pulse, it is coming 1. So this Q1 will become 1 when the first edge of this clock pulse comes, and it will be remaining in the same state until the next clock pulse. So it will be remaining in the same state until this next clock pulse, and then it is going to 0, and it continuously 0 until this point, and from here it is going to become again 1, and it continues. And for Q2, For Q2, consider Q2. So for Q2, the value is for first two cases it is 0. So even after first edge of the clock pulse, first clock pulse itself, so it is still it is 0 for the first clock pulse, and the second clock pulse it is going to become 1. So it will be 0 for the first clock pulse. So initially it is 0, then it is 0 for the first clock pulse, then it increases or rises to 1, and then it retains its position, its value, and then it is coming back to 0 and continues in that state. And for Q4, sorry, Q3, it is always 0, almost always 0. But when it is this fourth edge comes, sorry, the third edge comes, that is going to become 1, this one, and this edge comes, this one is going to become high, Q3 is going to become high, and it retains at that in that state until the next clock negative edge like this, and it will become 0 from there on. And if you continue this clock pulse, then you will be having again values corresponding to Q0, Q1, Q2, Q3, Q4, etc. But up to this third clock pulse, we have 4 states, and then it repeats. So let us give the values corresponding to these different states. So here we are having Q0, which is 1. Then here it is 0. Q1 is 0. Q2 is 0. Q3 is 0. For the next clock pulse, Q0 is, so initially this is 1, okay, until the first negative edge of the clock pulse. And then Q0 will become 0. And this will become 1. And this is 0. This is again 0. Here it is 0. This is 0. This is 1. This is 0. It is again 0. This is also 0. This is 0. This is 1. So basically, we will get the same pattern as you can observe in this table. We are having 0, 0, 1, first 0, 0, 1, then 0, 0, 1, sorry, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0. And if you go further, then you can see it is repeating. Again, you will be getting 1, 0, 0, 0. So this is the explanation of ring counter or shift register counter. So far we have discussed the shift register counter, and we observed that the number of states for this ring counter or shift register counter will be equal to the number of flip-flops, and we also discussed the truth table corresponding to this particular ring counter, and we also discussed the decimal equivalence of these 4 states, and then we plotted this pulse diagram. Okay, now we will move another ring counter, which is called as twisted ring counter. Move to the top. The next one is twisted ring counter. For this twisted ring counter, the diagram is same. Very small difference is there for this case. Very small difference. So we are again considering 4-bit case 4-bit counter, so it is 4 flip-flops will be there. Will be 4 flip-flops. Maximum number of decimal points or the decimal equivalent number that you can get from this kind of 4-bit counter will be 16. Number will be 16. So up to from 0 to 15 we can get by using 4 flip-flops, because we are considering 0, 0, 0, 0. So we are having 4 bits. If you consider the maximum of this 4 bit, then it is 1, 1, 1, 1. So if you multiply that with 2 raised to 0, then you can consider that 1 into 2 raised to 0, 1 into 2 raised to 1 plus 1 into 2 raised to 2 plus 1 into 2 raised to 3. So this is 8 plus 4 plus 2 plus 1. So basically this is 15. So from 0, this is nothing but 0. 0 to 15 you can get by using a 4-bit counter. Okay, so any counter if you are using with 4 flip-flops, you will get values or the decimal values, decimal equivalent values up to this 15. Okay, so you have to consider that when you are using 4 bits, then you will be getting 0 to 15. If you are using 2 bits, then we will be getting only up to 3. 0, 1, 2, 3. 4 gates or 0, 1, 2, 3 you will be getting. If you are using 3 flip-flops, then you will be getting 0, 1, 2, 3, 4, 5, 6, 7. Up to 7 we will get. Total we will be having 8. In this case, total we will be having 8. That is from 2 raised to 3. Maximum number is 2 raised to 3. That is 8. Maximum number here it is 2 raised to 2. That is 4. 4 states we will be getting. Here we will be getting 8 states from 0 to 7. Here we will be getting total of 16 states from 0 to 15. I hope you understood that. So now we will be considering another ring counter, which is having similar circuit diagram, but a very small difference in there. So let's consider again D0, D1, D2, D3, and we have Q0, Q1, Q2, Q3. And this we are considering synchronous counters now. We are only considering synchronous counter. So first synchronous counter that we discussed is the ring counter. And before that, we already discussed the 2-bit counter also. So, and this is the twisted ring counter. Okay, this is also called as Johnson's counter. Sometimes they will ask like this, Johnson's counter. So in this case, the difference comes like we are having Q0 to D1. Q0 is given to D1, Q1 is given to D2, Q2 is given to D3. Okay, and the only difference that is coming in this particular case is that we are taking Q3 bar into the input of the first flip-flop. So from the last flip-flop, the complement of the output of last flip-flop, which is taken into the as the input to the first flip-flop. That is the only difference that we are having in this twisted ring counter or Johnson's counter. So here we will be having this clock. Okay. And also we are having the all other connections But here one more difference is that we are having the clear or preset option here, clear or preset. Here also we are having that clear or preset. But the difference is that clear or preset, and the difference comes, we do not have any preset connection here. So all the values will be cleared initially. So we have this connected to here. So this is nothing but that clear option. Okay. Here, whatever we are having here. So I will this, and here also I'm having. So all flip-flops are cleared because we have given this connection at the bottom, which means that all these are clear state. And when you are having that clear, which is enabled, then all the flip-flops will be cleared. So initially all the flip-flops will be cleared. So that means in your output, so we have to consider it like this, as we discussed earlier, we will be having clear or preset, okay, clear or preset option. So when this is 0, this means that your clear is on, because we have given a note here. So 0 noted here, it will become 1 when it enters into this flip-flop. Okay. So this is 0. This 0 means irrespective of your clock pulse, will be having Q3, Q2, Q1, and Q0. All of these memory values will be 0 because of this clear. We are connected all the flip-flops to this clear option, clear connection. Okay. So that all the values will be, all the memories will be cleared and it will be equal to 0. Now when you are having this clear which is equal to 1, now the clear is not enabled, or clear function will not work. So at that time, if you are having that clock pulse at the negative edge, and then for this case we will be having. So this case, what will be coming? So in this case, this will become Q3. So you can see from here. I will explain that. Currently Q0 is 0, Q1 is 0, Q2 is 0, Q3 is also 0, Q3 is also 0. But what is this Q3 bar? Q3 bar is 1. Q3 bar is 1. So that one will be going through this connection. It will be going through this connection, and it will be coming to this D0. That one is coming at this D0. So initially all of these Q3, Q2, Q1, Q0 are zeros. For the next clock pulse, for the first clock pulse, first negative edge, this Q0 will become 1 because we are having 1 now here, and that is the input of this first flip-flop. That will be shifted to this Q0, that is the output of the first flip-flop. As you know, this D flip-flop will be having same output as the input. Okay, so the D0 value 1 will be shifted to Q0 when this first negative trigger or negative edge of the clock pulse arrives. So Q0 will become 1. Okay, all other values are 0 because this 0 will be the value of D1. Okay, and that D1 will be shifted to Q1, then that will become 0. Similarly, Q2 also will be 0, Q3 also will be 0. Okay, so when Q3 is 0, again you can see this Q3 is 0 here. So your Q3 bar will be again 1. Q3 bar will be again 1. So next time Q0 will be again 1 because still your Q3 is 0. Q3 bar is 1, so this one is again going to this D0, and that will be shifted to Q0. So Q0 will be 1 again. At the same moment, Q1 is now Q0 is 1, and that one will be shifted to D1, and that will be shifted to Q1. Okay, which means that this is Q0 is 1. That means D1 is 1 now. That is connected to D1. Q0 is connected to D1. So D1 is 1. So when the next clock arrives, that D1 value will be shifted to this Q1. That is the output of the second flip flop. That will be 1. Okay, so Q1 will be 1, and Q2 will be 0. Q3 also will be 0. So this is for the next clock. And still you have these values. Again, you can go on. For the next, still your Q3 is 0. Q3 is still 0, which means that your Q3 bar is 1. So again, Q0 is 1. Okay, Q1 also will be 1. Q2 also will be 1. And Q3 only is 0. Again, if you consider, this will become 1 next clock pulse. If you consider edge of the clock pulse, this is again 1. This also will be 1, and this also going to become 1, because your Q3 bar is 1 even at this clock edge of the clock pulse. Okay. Now, if you further move, then we'll be having the next clock pulse edge. At this moment, your Q3 is now 1. So Q3 bar is 0. Q3 bar is 0. So this 0 will be shifted to this D0. So for the next clock pulse, Q0 will become 0. So for the next clock pulse, this value will be equal to 0, and all other values will be 1. And this 0 will be shifted. So still Q3 is 1. Okay. So again, your Q0 will be 0. Since Q0 is 0 for the previous state, so this is 0, which means that your D1 is 0. D1 is 0. D1 is 0 means your Q1 also will become 0. So Q1 will be 0 here. This 2 will be remaining 1. Again, Q3 is 1. Q3 is 1 means Q3 bar is 0. Okay, that will be given to D0. And again, Q0 will be 0. This Q1 will be 0. This time Q2 also will be 0, but Q3 will be 1. And for this clock pulse, Q3 bar is still, which is 0, because your Q3 is 0. So that Q0 is again 0, Q1 0, Q2 0. Now this time Q3 also will be 0. I hope you understood this table. If you have any doubt, you can ask. So you look at this state. These two states, they are same. These two states are same. So it is starting to repeat these states from now onwards. Okay, from here onwards, it is starting to repeat its states. The counting, it starts repeating. So we have a total of 8 states here. So this is corresponding to 0, 1, 2, 3. Sorry, this one is 1. This one is 3, and this one will be 2 raised to 4, 6, 7. This is 7. Then this one is 15, and here it is. This one is 14, and this one will be 12. This one is 8, and this one is again 0. So we have this many number of states with the Johnson counter or twisted triple counter. So how many states are there? 8 states are there. 8 states are there. Now, if you consider the number of states and number of flip-flops, okay, in this twisted ring counter or Johnson counter. So in Johnson's counter, number of states equal to 2n, where n is the number of flip-flops. In previous case, when we discussed the ring counter, it was having the number of states equal to number of flip-flops. That is, number of states will be equal to n. But here we are having number of states equal to 2 times n for the Johnson's counter or twisted ring counter. Okay. So this particular circuit will be counting the clock pulse like 0, 1, 3, 7, 15, 14, 12, 8. Then it starts repeating this 0, 1, 2 like that. So you can see that this is not a continuous progression, as you can see from here. It is a random fashion of counting. This is possible when you are using this synchronous counters. Okay, in a synchronous counter, we cannot see such kind of random behavior. Okay, so we are having this Johnson counter. Now you can plot this pulse diagram. So I'm not going to draw it right now. You can draw it by yourself. So you have to consider the clock pulse first. Okay, and make all the values initially. All the values are 0, Q0, Q2, Q1, Q2, Q3, all are zeros. Then Q0 will be 1 for next clock, 4 clock pulses, and then it is going to 0 again. Okay. Similarly, Q1 will be 1 for 4 clock pulses after the first edge. Okay, so I will just show that. I don't think that is necessary, right? Because you can draw it by yourself. I will just show here. I will just show some 1 or 2 of them. So we are having this clock pulse like this, etc., and we have this negative current. Now before that, we are having that clear. So clear will be 0 somewhere here, and then it is maximum. After that, there is no clearing. This is your clear or preset option, and this is your clock. Now if you draw for different memories, that is Q0. So Q0 will be 0 up to this first clock pulse, because all are 0 initially, and then it will be going to become 1, and it will continue in 1 for the next 4 cycles, 4 clock pulses. 4 cycles will be going like this, and it is continuously 0 for the next is 4. And Q1, if you consider, it is also 0 initially, and it is going to become 1 for the second clock edge, clock pulse edge. So it is starting from here. It is going to become 1 for the next 4 clock pulse edges. So 1, 2, 3. So this is up to 4, up to 3. So up to this, it will be 1. Then it is going to become 0. Again, if you go for Q2, it is 0, and this clock pulse edge. And becomes 1 here, continues in that state until this clock pulse edge arrives almost here. And Q4, Q0, Q1, Q2, Q3, we are having 0, 4 zeros, right? Yes. So it will be starting from somewhere here. I hope I'm drawing the right way. So this will be 1, and it will continue in 1. So you can complete this. I just draw I have just drawn this 1, 2, 3, 4, 5, 6 edges only. So there are many other 1, 2, 3, 4, 5, 6, 7, 8 are there. So you can draw up to that or up to 7 edges you have to draw at least to get the complete picture. Okay, so I'm just showing how it will be. From this, you can also denote the numbers, values of each of these states Q0, Q1, Q2, Q3. So this is 0 initially, 0, 0, 0, 0. Then we are having 1 here, 0, 0, 0. Then again 1, 1, 0, 0, 1, 1, 1, 0, 0, 1, 1, 1. Then 0, 0, 1. I'm talking about this one. This also 1. And again, continuously you can do all the values. Okay, so this is all about Johnson's counter or twisted ring counter. Okay, now we will move to the asynchronous counter. Now let me see whether we have something else in this cascading. And then, okay, we will move to this asynchronous counter. Okay. So in the case of asynchronous counter, as we discussed earlier, the clock is not directly connected to all the flip-flops. It is connected only to the first flip-flop. Okay, that we already discussed when we differentiated this synchronous and asynchronous counter. Okay, so we will discuss the asynchronous counter or ripple counter. It's also known as ripple counter. So I'll just explain what is this ripple counter. So we will discuss now with this ripple counter. Ripple counter or asynchronous counter. Okay, ripple counter or asynchronous counter. So in this case, we will not connect the clock pulse to all the flip-flops. Only for the first flip-flop, we will be connecting this clock pulse. And the remaining clock pulse, the remaining flip-flops, the clock pulse will be given as the output of the previous flip-flops. Okay, so let us consider a 2-bit ripple counter. So we are considering 2-bit ripple counters. For 2-bit means we need 2 flip-flops. Okay, let's consider JK flip-flops. So we need 2. So you can design all this with the JK flip-flops or T flip-flops, T flip-flops. Okay, and so we have JK flip-flops here. Okay, and the diagram will be like, as we discussed earlier, we have diagram for this particular asynchronous counter or ripple counter. We're having J values, K values like this. And the rest is this. Okay, so this one will be connecting to this. This is J0, and here we will be having K0 for the first flip-flop, K0. This is J1, K1. We have Q0 here, Q1 here, and we have the Q0 bar and Q1 bar. And the first flip-flop will be having that clock. Clock is connected here like this. Sorry, this is not required. So this is the clock which is applied to the first flip-flop 1. And for the second flip-flop, the clock is applied from this Q0. So it is going like this. So the clock is nothing but this Q0 for the second flip-flop. This is flip-flop 2. Now you can see this one is connected to J0, K0, J1, K1. So this is nothing but the logic 1. This is logic 1. So when you are having this logic 1 for your J and K, then that will be in the toggling state. Okay, also we are having this clock pulse. So this flip-flops will be in toggling state if it is having the clock pulse which is equal to 1. Which after this inversion, after this NOT gate, if it is going to become 1, then you will be having this toggling of this output Q0 and Q1. Okay, and this Q1 is the most significant digit. Okay, so we have to take the output from this Q0 and Q1. So this is your first output, and here this is your second output. So this is Q1 and this is Q0. These two are the outputs. We are considering 2-bit counter. Okay, now consider the same. So Q1 is the most significant bit. Q0 is the least significant bit. So we have to write it like this. And we have the clock pulse. Okay. So initially, let's consider initially this Q1 and Q0 will be 0 when you are not having that clock pulse and all those things. Then this 2 will be equal to 0 at that moment. And when the first edge, negative edge of your clock pulse arrives, what will happen? So this clock pulse is applied on this particular flip-flop, only this first flip-flop. So when the first inverse clock pulse arrives, negative clock pulse, negative edge arrives for this, it will be acting only for this first flip-flop because this second flip-flop is not connected to the clock directly. Okay, so this first flip-flop will toggle its state, and Q0 will become Q0 is 0 now, that will become 1. At this moment, this will be equal to 1, and this is again this will be equal to 0 because the second clock pulse still having that Q0 value which is equal to 0. So for the first clock, when the first clock pulse arrives, was the edge of the clock pulse arrives, then the flip-flop 1 will be toggled, or its state output will be toggled, and still at that moment Q0 will be 0 initially, so that will be given to the second flip-flop as the clock pulse, but that will not make it toggle to its state, that particular state. Okay, so initially 0 0, it is at 0 0, and in the next for the next clock pulse, this will be the first clock pulse, it will be 0 1. So I think that will be, and this will be Q0 0. This one is the clock pulse is in the negative edge, and this is coming, so this will become 1. So clock is 1, J0, K0 1. So this Q0 will be toggled to state 1, right? Yes, in this time this Q0 will be going to state 1, and this 1 will be given here, so this will be 0, right? So this one will be given here, so this will be 0. If you take the note of that, it will be 0, so that this Q1 will not be toggled, so that will be remaining in this scene in the same state. And for the second clock edge, we are having this state is now 1, Q0 is now 1, and that one is given here, one is noted here and given to this flip-flop, so that this Q1 will be 0, that is not toggled. For the next edge, clock pulse edge, this again going to become 0, because we are having again the next clock edge, the output of the first flip-flop toggles again for the next clock pulse, so that the Q0 value will become 0. And when that becomes 0, the clock of this second flip-flop will be active, because it is noted. Okay, it will become complement of this output of Q0 because of this not operation here, and that will become 1. So now the flip-flop second will be having clock 1, J1 also 1, K1 also 1, so that the flip-flop second flip-flop will be toggled. So Q1 will be toggled and we will be getting 1 here. And for the next clock pulse edge, again the Q0 value will be toggled, but at that moment your Q0, this Q0 will be toggled. As you can see, this clock is directly connected to this flip-flop 1, so that when the next clock pulse comes, clock pulse is inverted clock pulse. Okay, negative edge we are considering, so that it is inverted. So it is complement will become 1, and clock is 1. Okay, J0, K0 or 1, and again Q0 will be toggled. Q0 will become 1. So when Q0 will become 1, this is going to become 1 here. So when it is going to become 1, this pulse, this clock pulse will become 0. Okay, because we have to take complement of that at this point. Okay. So complement of that particular Q0 will be applied to this as a clock of this flip-flop second, as we have this not here, not operation here. So we'll be having 0 at flip-flop 2 as clock, so that it is not going to toggle, so that it will retain its state as 1. Now, if you consider the next clock pulse, what will happen? Q0 again toggles, because it is directly connected to clock. So it will toggle to 0, and that 0 will come to this Q0, and Q0 will be equal to 0, so that it will be complemented and applied to this flip-flop, second flip-flop, so that it will become 1. Clock is 1, J1 is 1, K1 is 1, so this is going to become toggled again. Q1 is also going to toggle. Now, if you consider the states, you can see that it is starting repeating. It starts repeating as the first state. So it is starting. So the number of states that is passed by this counter before starting or before it is reaching its initial position, that is the states available for this counter. So here we are having total of 4 states. We are having total of 4 states. Okay, and the decimal equivalent of these states, we are having here, it is 0. This one is 1. This is 2, and this is 3. So 0, 1, 2, 3 we are having. Okay, so this we already discussed when we differentiated the synchronous and asynchronous counter. From here we can see that when we consider the asynchronous counter or the ripple counter, we are having a fixed count sequence. Okay, fixed count sequence is possible in the case of asynchronous counter. We can see 0, 1, 2, 3 like that, and also we can see the progression, that is from 0 to 3. For each of the clock pulse, if you consider, the progression is from 0, 1, 2, 3. So it is starting from 0 and reaching at 3. So this is a up counter. So 2-bit up counter. So this is a 2-bit up counter. We can say this is a 2-bit up counter.